All right, so today we're going to catch up again on the next step to using the things like the rate equations and reaction progress. We'll start transitioning over now into using these tools as ways to generate hypotheses about interrogation of reaction mechanism. So we're going to talk a little bit last on some of the derivation stuff we left off on, and then today we're going to do the intro to how to use COPASI. So this is a program to do visual tools for reaction modeling. Quick other two notes. So first of all, I mentioned last class, there's a paper I want you guys to be aware of. As I go through class, if there's something we will come up in class, I'll make it explicit, like we will go over some part of it, whatever. For that paper, I want you guys to download it, read it, know about it. It may come up in things like midterms or other assignments, so it's not something we're going to do explicitly. Just read it. If there are questions you have from it, happy to discuss, but it's not something I'm assigning of like, oh, you will be quizzed on this one, other than it'll be probably part of something that we do in our midterm. Next, same thing for the assignment. I just posted one up on Sunday. I'm going to try to do these infrequently, about every 2 weeks. And same point, I will try to release it on Sunday, and it is due the following Sunday. Now, these are not 4 marks. I'm not asking you to submit something for this that I'm going to go through and grade. This, think of it as a participation point. I'm expecting you guys complete them. I do expect you to turn in a part. I'll make that explicit of something you to turn in. And then the following day, I will go through and we'll talk through the answers to that midterm, or to that question. So it's posted up on the Canvas site right now. Let me know if you have problems getting to it. Assignment 1, let me just quickly jump over to it. Assignment 1 here is what I posted, and it has 2 pieces. Up here at the top, these are exercises. What I'm asking you to do here is do these. So I'm asking you to complete the derivation of the Michaelis-Menten enzymatic system. So we went over in class what those derivations look like. I'm asking you to do them longhand. So this is, you should probably go out and do 15 minutes of cardio every day. This is an assignment where I'm saying you should do this. I'm expecting you can do this. If you have problems on that, come and talk to me. But we won't review it further than telling you I'm expecting you can do that kind of derivation. So next is, again, please build a simple model in COPASI of a Suzuki reaction. We're going to actually talk about that here in class. I'm expecting you can go in and build that model yourself. So these are stuff that I want you to do, and just expect that that you're competent on them. The problems for submission, I want you to create one PDF, so a single PDF of all the stuff you're handing in. The PDF should be submitted to me by Sunday, about 5 p.m. And then we will discuss it in class. So we'll go through the answers there. Now, what I probably will end up doing is I'm expecting you guys to submit that PDF. I will go through them on Sunday. I will call on you guys of, this is your answer. What is your answer? Why is that your answer? And we'll discuss it. Again, this is not meant to be like a shaming or something like this. This is meant to be a discussion of how you execute them. This first part here is a very common thing that you will be asked to do. You have an overall reaction, you have 3 possible reactions, and you're going to carry out the steady state rate equation derivation for these. Once you can see the mechanism, this will start to allow you to come up with experiments that will allow you to validate which mechanism may be right. This is practicing going back and forth between the equations and what experiments you choose to set up. So we'll do this point. Second one too, in class we've discussed the Michaelis-Menten system, and we had the comment before. What does very large or very small s mean? Like if substrate is large, it looks 0 order. If substrate is small, it looks 1st order. I want you to build that system in COPASI, and then I want you to actually try for yourselves to say, what does large or small mean? Now, by design, I have not given you enough information to quantitatively answer this. This is welcome to the real world. You guys are 4th year / grad school. A big chunk of what I'm going to emphasize as we go through the class is at some point, you're going to have to make a good guess. You're not going to have enough information. So for example, if I'm asking you how large or how small does S have to be, I have not told you your enzyme concentration or your values for your Ks. You're going to have to come up with something that says, given the following assumptions, here is how I choose to answer this question. So this part is 2 parts. Practice using COPASI, but you're going to have to come up with some guesses for what these values are going to be in order for you to make any headway in this question. I want you to practice, start getting comfortable feeling like you don't have enough information to answer it. This isn't Jeopardy. This is practice doing sort of research questions, okay? Okay, any other questions on that before we jump in? Again, I want to underline that. The thing that happened in previous too is my expectation with these assignments, even though they're not 4 marks, you do have to hand them in. The barter we have is you guys are adults. I want you to please submit that material so we can talk through it. And absolutely, we'll be pulling these kinds of questions for things like the midterm and the final. So going through them has value to you guys for the next part too. Okay. We left off introducing the Michaelis-Menten equation. And again, I want to just highlight, like last time, there are two ways you can often see this expressed. Remember, any rate, dp dt, is equal to the last step in whatever your prophetic mechanism is. In this case, it's k cat times the intermediate, which if we do all the steady state derivation, you'll get this equation up here. So that's the step-by-step, call it normal organic chemistry mechanism that will give you this point. The simplification we did down here, this is if you're a biochemist and you say, what is the Michaelis-Menten equation? Usually you'll see it written this way, where we've substituted the formal rate constants, K, enzyme total, for things like Vmax and capital Km. Those are just rearrangements of these terms to make it into a simpler form for easy digestion. The only difference is if you're a biochemist, you might be used to seeing it this way. If you are an organic chemist or somebody who's doing catalysis, this is the more general one. What's nice about the Michaelis-Menten system in this more general one, it doesn't matter that it's enzyme. Enzyme is just catalyst. Could be palladium, could be protons. If you see little k1, little k cat, little k minus 1, we're talking about any catalytic system that follows this sort of single intermediate catalytic cycle with a reversible first step and an irreversible second step. So what's useful about this specific equation here is it's a blank slate for any catalytic system that has a single intermediate. And we talked about this about large and small. Again, part of the assignment, I want you guys to try and quantify how large or how small and under what conditions. Now, we walked through the basics of how to do the algebra. For a system like this, that's a single intermediate, it is still tractable. You can do the algebra longhand, depending on how quick you are, it may be fast or slow. This is the Python code. So who here has ever used Python for anything? Never used Python for anything. Okay, half and half. Right now, if you have never, go find somebody that has. They are now your best friend. It's not as bad as you think, and we will actually do we have one of our graduate students, Jayu, who's working on both his research but also his teaching component. He will have a Python tutorial of how to use this in a much more advanced way, so it's an introduction to coding. For right now, I want you literally to go connect up with somebody else if you've never done it. This script, if you were to copy paste this entire thing into this Google Colab paste, this is a Jupyter notebook, and in fact, you can link to this Jupyter notebook and save it in your own Google Drive to have your own copy of it to use as you want. It has individual cells for each one of these points and allows you to use or run each one of these code in this Google Colab Python space. So you don't need to install it on your laptop. You don't need to get your dependencies right. Following this link will give you to the shared Google Drive space. All you have to do is set up your own or share it to your own Google Drive so that you've got a copy yourself, or you can even manipulate this one online. The downside about doing that is that you mess it up for everybody else too, so it's better to save your own local copy. And then practice it. All this is doing is step one, you are bringing in this Python package called SymPy. It's basically stuff so that you can express, it's just visualization, so you can express the equations in that sort of ratioed way. You're then defining a bunch of variables. You're saying these things, what we're calling S, B, whatever rate, these are variables that you might use for your calculations. You have to define them as, these are like saying X, Y, substrate, unknowns, right? You then define 3 different equations. Now, these are the 3 equations that you need for your single intermediate catalytic system. CT, C underscore total minus int, and again, I'll show you on the next slide. This is the one part where if you've never done any kind of computer coding, it gets a little bit scary, because what you're doing here is you are calling these variables in a mathematical equation. You're saying CT is the free catalyst, the total catalyst in the system, and the intermediate concentration. So that's just the mass balance equation. Why this gets difficult for different people is one student may choose to define these variables as X, Y, and Z. And some other person may choose to call it CT, C underscore total, whatever. They mean the same thing. It's just that there's a vocabulary part where, because we've chosen, there's no real hard and fast rule for how these intermediates should be called. It gets hard to look at other people's code because suddenly you've chosen to make variables a certain way. The thing that matters the most from that is documentation. As we add and write things for code, you need to use language left over for whoever's reading your code after to make it interpretable. And this is definitely not perfect, but I just wanted it as a quick introduction. The steady state equation here, this is basically everything with the formation and destruction of that intermediate. And we're going to set steady state equals to 0. And then the final rate law, the last step, is just our kcat times our intermediate. Once we've defined these three ones, we can just say, solve this. Run a simple thing where I want it to do the algebra saying, given these representations and unknowns and these three equations, please go through and solve this point given a certain condition. Where the intermediate concentration, given that the steady state is equal, and intermediate change is equal to 0. So practice that for now, but just to kind of lock those pieces out, these three equations, that one there is our mass balance equation. This was on the previous slides we did before. We're just saying CT is our enzyme, C total is the total enzyme in the system, minus the intermediate was the ES. This is the equation for a steady state, which is this guy down here. That's the steady state rate equation. So steady state is equal to K1S and CT. K1S and CT in this case was just the notation we used for free enzyme. Kcat intermediate is the second step right here, Kcat and intermediate. And then K2 intermediate is just what we called K1 or K minus 1. One of the things about notations in Python, this is where unfortunately it's an inexact point. In our normal way of representing this is little k with a subscript where k minus 1, what we're saying is it's the reverse reaction to k1. The problem in Python is we can't use subscripts. So we call things, k1 no subscript. We can't add a minus here because if we said k minus 2, that means k subtract 2. We can't use the negative sign because there's no way of denoting it as just a text string. So unfortunately, that's where there's not a perfect one-to-one overlap. We're up here, again, the normal system, we said k1, k minus 1, and kcat. Those have now turned into k1, k2, which is the reverse equation, and kcat for this. But again, you are free to use any notation system you want. Just follow something that makes sense, especially internally yourself. And again, this is why talking it through with other people, seeing how they've chosen to do it is very valuable for yourself too. Final one is the rate equation, which is just dp dt is equal to kcat times intermediate. That's this one here. If you use these lines of code up here with those three equations I've shown here, it will spit out, that Google Colab sheet should spit out this. Now, if you notice, this is what Python gave. And if you match it over here, we have K1, which is K1, Kcat, and Kcat, C total, which is your enzyme total, and substrate, which is substrate. So same numerator, same denominator between the two. So this is, again, all this is a very simple algebraic tool. Now, if anybody's used Mathematica, or has anybody used any other packages for just doing algebra for you? There's MATLAB, Mathematica, Maple, what's that? R will do it too, absolutely. These are all languages for doing the simple hierarchy of move, sub, right? Like Python, all computer science is just applied math, really. So this is one way of doing it. So the exercise for now is, 1, go through and do this longhand. That's part what I'm asking you to do for the exercise. 2, try using the Colab sheet. And again, if it's really easy for you, I want you guys to connect to other people in the class. Teach somebody who can't do it easily too. This is not required. It is a very useful tool. It's a skill that you can teach yourself. So we left off in those parts. Now the thing I want to emphasize though is, let's say again for the assignment, I've asked you to go through and figure out what the order is, like when we actually talk about this part. This is a graph of the rate that you're observing against the substrate concentration. And this is the overall, like the rate here is a value. That's what we're plotting here on the y-axis. And S is equal to our x value. So really this curve here is showing rate, the calculated rate, given some values for S, where we've also made some assumptions of what Vmax and Km are. So those are constants, and then we're varying S as we output this. So Does everybody know how to use Excel? Oh, you guys giggle, but sometimes no. This is something that we grew up. I actually had a book handed to me when I first started called Excel for Chemists. Is a really, really useful part because nice thing again, Excel is one of those very easily accessible tools that lets you, it's kind of like two electron mechanisms. You can play this game of what if. So I can actually take an Excel sheet and say, given some values for S where Vmax and Km are constant and this relationship, I should be able to populate a whole row of given some S, what's the rate? Given some S, what's the rate? So I should be able to empirically create this curve given any of those two. Does everybody feel confident that they could do that? Who does not confident they could do that? Okay, definitely become confident. I see a volunteer behind you over there. But I mean, like, again, this is what's great about this is if you ever have questions like, how big could my error be? Or if given, let's say, some speed of a reaction, could I ever observe this intermediate? You can create in Excel a reality thing based on this first principles and visualize it yourself. And again, that's what we're going to practice in COPASI. But one of the things you can do too is if you imagine trying to do this experimentally, not by Excel. If I tried to create this, usually what you would do is execute many experiments according to the method of initial rate, plot or measure the initial rate of a reaction, and that becomes one data point here. So you'd set up a whole system, you choose a single enzyme concentration, a single temperature, you would try the reaction with some substrate concentration, measure the initial rate, throw the whole thing out, start again, do it again. So what you're usually going to do, and again, has anybody ever done Michaelis-Menten measurements before? Usually what you have? How much fun was it? It was in biochem? But did you enjoy doing it? You're a weird individual. The issue is, right, normally this is a case where the perfect curve shown here is for possibly billions of individual substrate concentrations. There's a limit where there's a certain number of either concentration of enzyme, whatever. You're going to make a call that says, I need to do a certain number of experiments in order to fit it to this function to measure these values. I may not know a priori either, where this bending is going to happen. So I may not even know what value of high substrate concentration is even applicable for my system. So it becomes iterative. You try it, try higher, and you're looking for a behavior, and you're assuming that this equation holds for your entire system. And there's a lot of reasons why it's difficult. Usually you have to go through and do it in triplicate. My point is, you will usually end up doing some sampling, call it 10 or 15 across this point, and you're hoping that your data fits to that. And that may or may not be the case. So your initial rate measurement, again, everybody's done or at least heard of the method of initial rates, right? Why do we use it? Like, what's the reasoning that you've been given for why do we use the method of initial rates? Why do you think we do? Yeah, you're setting up an experiment, A and B. You call go, so you have a really good idea of when it started because you started it, when things come together, so it's an easy place to put the stopwatch on. You're measuring either the loss of starting material or the formation of product in those first small amount, 5 to 10%. And all you're doing to pull the rate out is, I got a couple of changes over time, I draw a line through it and say, that is my initial rate. The slope of whatever that initial line is equals the value I'm trying to extract. So operationally easy, you know when your T0 is, you know when your slope is. The other big one too, and we talked about this before, why does C, this curve in C start to taper off? Why does it slow down over time? Two reasons, major. Product inhibition or running out of fuel, starting material loss, right? Initially, we have no product. Initial rates are good because we're assuming that whatever complexity might happen over here, catalyst decomposition, changes in temperature, those are over the course of the reaction, and at least we hope that we can control that it's simpler, that the assumption that the initial rate is representative of the real thing is true at the very beginning. So that's why we usually go to it. And again, it's operationally simple. Start an experiment, measure the tangent, pull out a rate. Change some initial concentration, A, hold the other one constant, measure the rate. Based on this, what would your conclusion be for order in A? Yeah, first order. Doubling the initial concentration of A, doubled the rate, it has a one-to-one relationship, seems to be first order. We add a third experiment where I hold A constant between experiment 2 and experiment 3. I double B, so what's the outcome? What's the order in B? Everybody see that? You're very familiar with this point. That's normally what we would do, right? You need at least, in this case, a reference state, a variable, and a second variable where the composite, all three of these, will say the same thing. If you notice, experiment 1 versus experiment 3, I'm doubling both. What happened to the rate? So that's consistent with the idea that I have a second order process overall, right? Doubling A and doubling B led to a 4, so 2x times 2x equals 4x, seems like it's second order. The problem is, if I only looked at 1 and 3, I can't authentically say it's first and first. It might be second and 0. It could be 1.5 and 0.5. This is where all three of them gives you unique matrix to sort of talk through this point. So that's what you've gone through. Now again, if you had to do this experimentally, this is a lot of work and time. What I'm going to show you now, we're going to jump over to COPASI, which is creating a synthetic reaction system. So if you have your computers, bust them out now. You can walk through this. If you find it's easier just to watch what I'm doing, remember, I'm recording all of this so you guys can watch the video after, whatever works better for you. Doing it live versus watching it and then playing it back after, whatever of those two is better for you is useful. Okay. Again, I have the Mac version, so it may look a little bit different on PC. The way COPASI works as a project is you have this little like region over here, and then this is where you do your manipulation. You introduce like your variables and other components. The way it works is you've got these drop-down menus. So you just push the little caret, and it drops down to expose other subtopics. The main ones you're going to be using is model. Model is where you create your reaction sequence. This is where you go through and say, here are the steps, the elementary steps I'm going to consider. Tasks is where you run or manipulate, you basically create a synthetic reaction. You say, I am trying to do a calculation or a time course. The main ones we're going to use is time course, later parameter estimation, and possibly parameter scan. Those are probably the big three that we're going to work through, but today mainly time course is what we're going to look at. Output specifications matter. This is what COPASI shows you. So these are how you create graphs. This is what you graph what against what. So let's start at the top under model, and we're going to click down under biochemical. Again, this was created as a way of doing synthetic enzyme pathways, so it has sort of a flair that's focused on modeling enzymatic systems. And if you go down here to reactions, you can see right now in this model, since it's a brand new one, I haven't loaded anything, there are no reactions in the sequence. So what we're going to do is I want to create the Michaelis-Menten system, right? So part of this too that can help out, a good example or something to always keep track, if you're building a COPASI model, first thing you should do is draw the sequence in ChemDraw that you actually want to use as a guide. So I start off by saying, I'll do this on the board. We have enzyme, and I'm going to have a reversible reaction where I'm bringing in my substrate. That's going to make my intermediate, what I'm going to call enzyme substrate, and then I have a return and formation of product. Drawing out your guide is really good first because this means I can see I'm going to be creating 1, 2, 3 steps. Right? I have 3 reactions. The forward reaction from enzyme to enzyme substrate that uses up the substrate, the reverse reaction, and my product formation. And I'm going to label them as K1, K minus 1, again, this is your notation, and then K cap. It's usually what we call in the normal enzymes, the normal Michaelis-Menten system. Okay, these are your 3 steps. So we need 3 reactions. I'm going to go down over here, say new. You see it pops up and says new reaction. I'm going to double click into this, and it's going to open up a new window where if you notice over here, the reaction right now, so what we called here reaction, This is the name of the first step. And and again, following, it's really, really good idea to follow a sort of, come up for yourself the sort of a very rigid way of doing this. I'm going to call this one step 1. You can call it reaction 1, you can call it whatever, but I'm up here at the top. I've created a reaction. I'm going to call it step 1. This is the name here. So this is you keeping track of the individual steps. In the reaction tab right here, this is the steps, the stuff that's going to happen together. So I'm going to use the notation I've drawn out here on the board. I'm going to say enzyme plus substrate, and it is an equilibrium, so I'm just going to use equals, and then product, which is just ES. Now, whatever you type here, if I say ES in capital, and then another step I use ES in lowercase, it will think those are two different things. So case matters. So what I've got that together, I go down here and click commit. What you'll notice is it's got now 2 steps where it's saying K1 and K2. With those 2 steps, the first step uses enzyme and substrate with K1, and the second step, enzyme substrate, the intermediate, goes back with K2. So in this one step here, I've created both of these. That's all in case. Now you could do this as one way only. I could define just the forward reaction and then just the reverse reaction. But what I've done here by giving this equal sign is I'm defining it as a reversible reaction, so you only have to enter it once, right? Now what notice here is, like I said with just nomenclature, even though convention in organic chemistry would be K1, K minus 1, it's labeling this as K1, K2. Now one of the annoying things about COPASI, every single step will have a K1, K2, which means you have K1, K2 associated with the first step, K1, K2 with the second step. So don't get lost, as we don't index the subscript with these rate constants in this system. Okay, I'm going to go over here. So this is, yeah. Commit is down here. Yeah, you can also push enter, like you can just type it in this way and push enter, and that's also commit. But any changes you do over here, you push commit. And it's got the same thing working on like other developer environments. If you type in a syntax that it does not understand, like I missed these spaces or whatever, it usually just flags it as red. It won't populate this over here.
So the spaces are important.
Spaces are important. If you write this here, like I'll try it like this, E plus S equals ES, and it's like, I don't know what you mean, right? Oh no, actually no, this version's smart enough, it's added those spaces back into it. Okay, so that's our first step. Yes? Yes? Yes, we'll go into it a little bit later. Usually for all enzyme or all equilibria, I choose mass action. It may have just, depending on how it was answered, it may have just gone for constant flux. That's kind of like how it's going to treat it will change how it's going to treat parameter estimation later. It's not going to affect how the sort of the basic stuff you're doing here is, though. It will affect things like dynamics measurements, how fast it reaches equilibrium is another tunable. But generally for equilibrium, I always use the mass action one, and you're right. Sometimes, again, this is a free program. It can be a little bit buggy. Sometimes you'll enter an equilibrium, it'll just be like, you know what, constant flux. So you may have to change it back over. Just in general, if any of you guys are working with COPASI, you come up with let's say a COPASI file that's not working for you, attach it to an email, send it to me. I can bust it open, or we can share it on the Canvas site so that we've all got references as well too. It's usually silly things like this that you just got to look down. Okay, this is the first step. I'm going to go over here to the second reaction. You see right now it's got a warning because it's not populated. So I'm going to call this one step 2. And for this one, it's now this second step. It's enzyme substrate, kcat back to product. So if you're ever, one of the things that's useful too is if you put this drop-down menu of your species, what's nice about that is you can see what variables, what things we have created. So if you ever forget a name for what you called, let's say the intermediate, having this tab open here is very good because you can see I called the intermediate ES. If you called it int or int1 or palladium whatever or Bob, it's easy to see it in that point here. So this is ES, and it's going to be an irreversible reaction. So to divide that, I go left like a dash, and then greater than sign. So you do a little arrow. That is what you use for an individual reaction, and then I'm going to say equals product. And again, commit. Now, look at the equation I just created. Enzyme substrate, single reaction makes product. It only has one rate constant. It's still under this mass action. You can see it's now irreversible. What's wrong? I did not add the enzyme. The number one thing that people mess up, especially for large multi-chain systems, I can say, okay, enzyme and substrate makes intermediate. Intermediate with KCAT makes product. And I forgot to regenerate my enzyme. This program does not understand chemistry. So it'll let you do anything. You are not bound by physical reality. So just because I did not add enzyme here, I can still have a model that's kind of working, but it won't function like an enzymatic system because it's stoichiometrically using up my catalyst. So to be true to what we're trying to do here, I have to say product plus enzyme. Whoop. Product plus enzyme. And then commit that. If you ever want to check it, something I like to do, especially if I'm making catalytic systems, I go over here to my species, I click on my enzyme, and you can see it will show you where is that species being used. So it's being used up, enzyme plus substrate makes intermediate, and the second step, enzyme substrate regenerates product. For any catalyst, you should see it being used and regenerated. Versus something like product only shows up in our second step, or substrate only is used up in our first step. So you can actually go through and see where they're aligned. You can go nuts in terms of complexity of what you can build out here, but this is why I practice with this for your guideposts first. Anything else we think we have to add right now in terms of the steps? Yeah. Yeah. Yes. Yes, so the other way you could build this is you could say, step one, I want an irreversible reaction of enzyme plus substrate irreversibly to ES, and I'm going to call that mass action irreversible. Then I'm going to create another step, which is enzyme substrate irreversibly to enzyme plus substrate. So define them as two separate steps with two separate rate constants, both of them being irreversible. Same thing. The outcome will be the same. The one value of kind of binning them into one is when it does things, again, like parameter optimization, or you can play with values. Doing it this way, K1 and K minus 1 are coupled together. I can work with them as kind of a ratio directly. The way you're going to do it, if I really wanted, let's say, to manipulate the capital K, the equilibrium constant, and if I've separately defined them as two separate irreversible reactions, I'm going to have to create some math somewhere else in this model that links them together so that I don't just change the numerator and not the denominator, for example, right? Both work, it's whatever visibility has to. Again, the value of this is you're kind of unbound to do whatever you want. The downside is it can get a lot more complex keeping track of things too, that's all. So that's that first part. We now have a system. Number one, when working with this, it's a bit of a janky program. Save frequently. It will crash randomly, and especially if you've been building up a lot of different things, it will tend to break on you. So I usually will, when I'm working on a new project, I create a web, like a separate folder. What did I call this? Yeah, example 1 CPS. I create a separate folder as part of my project folder. I put all my COPASI files in there and anything associated with different ones too. So if you have real data, I put them all in the same sort of folder associated with the mechanism models that we're using. Okay, last one up here in the biochemical I want to point to is parameter overview. This is a single snapshot of everything that's in the system. Up here, this top part, these are the initial concentrations, and by default, if you did not specify it when you wrote out the reactions, it will just say everything is 1 molar. So it's saying, for this model, I have 1 molar enzyme, 1 molar intermediate, 1 molar substrate, and 1 molar product. Okay, that doesn't represent a real system. I'm going to go through and define it, so you just click on the value. Product is 0, enzyme substrate, the intermediate is also 0, and I'm going to drop the catalyst concentration to something like 0.01 molar, or what mole percent? I told you never to use mole percent. What is that? What am I kind of saying? If my initial substrate concentration is 1 molar, 1%, right? So, but this is where this setup here says I have a 1 molar reaction and a little bit of catalyst. Now down here, these are your values for your K. Up here, 0.1, 0.1, 0.1. Again, by default, it just says 0.1. This is where I said back to thing to kind of keep in mind. Diffusion limited is kind of like 1 times 10 to the minus, 1 times 10 to the 9. Slow stuff is 1 times 10 to the minus 9. You can choose any value in that part. What's super cool about this is if I knew an equilibrium constant or a real delta G value, I can set that ratio to be directly representative. If you know a pKa, you could actually put the real capital K or the acid dissociation constant into this one. Now you have individual access to both of those Ks. So this goes back to, I could define them as 3 separate steps and really have the same point. I'm going to decide right now that this first equilibrium is going to be forward favored. I want enzyme and enzyme substrate to probably bind over here. So I'm going to say the forward equilibrium constant is equal to 10, and the reverse equilibrium constant is 0.01. Now, if I looked at this simple system, and I was trying to set it up so that K-cat was my rate limiting step, what would I have to do? If I've chosen that first one arbitrarily saying forward equilibrium constant for K1 is 10, the reverse equilibrium constant for this first step is 0.1. So what I did is I said that capital K there is 10 over 0.01. It's very product favored. Remember, that ratio minus RT ln KEQ or minus, that gives you a delta G value you can kind of put in your head. But what I have to do to step 2 to make sure that the second step is the rate limiting step? Then, yeah, the slowest number in here just needs to be here. So I'm just going to say 0, 0, and again, factor of 10. Just a first rule of thumb, doing everything by these multiples of 10 is a good way to kind of start. Yeah. All on you. Scientific notation is, again, this is a blank slate. You could, as long as it's not alphanumeric, like it has to be numbers. Like it could, yeah. Like if you did 10 caret, like 10 raised to the whatever, that should work as well. You can put it in and you don't have to hit decimal places. I'm not sure the exact syntax to input it to. The other way too, again, this is the GUI front end, like this is the graphical user interface. If anybody is a bit more sophisticated with Python, there's actually a Python package that allows you to script all of this in like a CSV file and actually directly install it or use it in a Python environment as well. We also have some students, Finn, in our lab that's trying to make a much more organic friendly version of this that's open access as well too. So the problem with this is always what happens with anything with coding. There are a million ways to do the exact same thing. So talking to different people is useful because you can pick up tips and tricks of how they've done it as well. Okay, now we've not only got a catalytic system, but we've set the initial parameters so that it actually could function. What we're going to do is we're going to jump down here to plots, and I'm going to click on here, this new plot, and I want to actually set it up. So the reason I'm doing the plot is the model exists, I could run it, I can't see anything until I have a plot. So the plot is your visualization. So down here under plot, like I said, plot, and under this, you double click on the new plot, comes up here. I'm going to call this one time course under the name. And over here, you're going to say, I want a new curve. What that brings up is anything in the model that could sit on the X and on the Y. Now this is, to me, this is super powerful. You are not restricted to just plotting concentration and time. You could plot rate and time, or anything that is that's in this system. You have a ridiculous number of things at your disposal that you can plot, and you can choose anything versus anything. This is very important for me because how I learned this idea, when we call it a dependent variable, whatever, this is really what we're doing, right? We're taking a graph and saying, in the real world, if I change y, what happens to x, or vice versa, right? It's a way of testing any function. So what we're going to do here, x-axis, I want this to be a time course, so we are trying to create a plot that is let's say, concentration of substrate and concentration of product over time. So this is kind of like if I was to run this experiment and actually sample it, what would this look like? So the x-axis is going to be time. So you push the down. Now it's not just time, it is the model time. What that means is as the model progresses or runs the iteration forward, this is what's going to be indexed on the y-axis, or x-axis, excuse me. Y-axis is going to be species, and it is the transient concentration. So if you look here, if I click on this and drop it down, it shows the 4 species that we talked about over here. So we have our enzyme against time, the enzyme substrate, the product, and the substrate. Now you could individually click on them, but the fastest way if I'm graphing everything is just highlight transient concentration. So I have y-axis is model time, sorry, x-axis is model time, y-axis is all of the transient concentrations, and push OK. And you'll see it has 1, 2, 3, 4 functions that will be populated. So we will have 4 things on the graph, each of them represented as the y-axis, which is your concentration, x-axis is your time. And then we're done. Commit that. And you can see it makes the update. It's called time course now. We're ready. So I'm going to go to time course. This is the task. So here you say how long do you want the thing to calculate for. So this is if I was to watch the reaction for blah time, in this case 1 second. And intervals is how many individual measurements do I want to make. In other words, if I'm going to run the reaction for 1 second, I want 100 small steps to kind of carve it up. So think of it as how chunky your reaction looks like. And the interval size here is 0.1. So these two, you can either define it by this or this, and it will calculate it out. So these, all you have to do is fill in 2 of these values, and the third one will be populated. So right now I'm going to say run it for 1 second, and I want 100 individual steps. And I just push run, and ta-da, I have a graph. This plot will immediately pop up because I created this plot down here. So if you had 10 different plots, 10 different windows will open up, whatever those happen to be, right? All right, up here at the top is 1, 2, 3, 4 species, so I can hide or show each of those things. So look at what's happening here. Product versus time, starting material versus time. Yeah, we got a reaction, right? I see some both elation and frustration. What's happening here is I'm showing product versus time. Or let me turn that one off. Yeah. So in blue, starting material versus time is dropping. Product versus time is raising. These two here, if I hide these ones, enzyme substrate and here, right? Sorry. Oh, I had it wrong. Doop, doop. These two, sorry. They're all hidden right now. That's product, slightly rising. That's substrate. You can see there's almost nothing happening with substrate, and there's almost no product. The reason why is I've only run it for 1 second. I've only run a tiny fraction of a second of the overall process. These two, there's my free catalyst, and you can see the free catalyst rapidly drops to 0, and the intermediate concentration rises up. All we're seeing there is in that first second, this first equilibria that we said is basically establishing. If we start the chemistry at this very low concentration, you can see over here, remember, the enzyme concentration was 0.01 molar, and it's dropping to 0. And the intermediate concentration is rising to 0.01 molar. So that's just showing this first equilibrium, the establishment of steady state happening. And from this, based on the K values that we've had, we've just said that in about 1 second, based on the K values and concentrations, we're reaching the steady state of that intermediate. Yeah, sorry.
Is there a button to like fit the plot to the screen?
Fit the plot to screen. You mean like blow it up?
But I know it like started zoomed out.
Yeah.
Is there like a button that like zooms it in automatically?
I don't remember where it is on PC.
There.
I know that you can sort of zoom in and out. I know that there's some like zoom out and stuff, or tabs up at the top. Yeah.
Out.
But for now, if you want to see just what I have, drop the product and the substrate. So click on those two. And there should be zoom out. It should rescale. Don't know.
So then I can like.
Yeah,
I can
you can
do
look
it
in there,
manually.
and there it is. Yeah, exactly. I don't, for different versions, I'm not sure where the rescale or auto scale is. Worst case, what you could always do is close the graph and reopen it, and it should replot it where it auto scales it again too. The last thing too is, again, only what you're using with this plot, everything you calculate, if you go back to here and we click on our time course, down arrow, the results, the values are right here. So you can always take these values, select it, these points, and put them into another graphical software such as Excel or whatever, so you can work on, or you can manipulate your graphs yourself after. Yes? Okay, so let's, we'll pause here for this. Let me basically look at your code. If you run this and you're not seeing this, any changes over time, yeah. Let me take a look at it. I don't know, it may be something that's either, again, specific or how your system was set up. The one piece I want to add, let's go back over here. If I go to my time course and I just need to wait longer, I'm going to go back to my duration and I'm going to add a couple zeros. I'm going to wait for 1,000 seconds now. And I'm going to go through. I will close this. An important thing about this is if you've worked on a graph and it has shown you that graph, close the graph, do your next run. So I'm changing the total duration, and then I click run. It will populate a new graph with that new value. It will still exist, like it will still do it. If I change this value, this graph will update. The problem I've usually had is I've slid the graph in behind something. It won't jump to the front or be shown at the front. So what I did here is I tried to run it much longer. And again, it doesn't look like much has happened. There's this very initial little blip. So if I hide my enzyme substrate, my enzyme, and only focus on product over time, you can see it's going. It's just that after only 1,000 seconds, we only have 0.001 molar in product. It is just tiny amount of product. Based on the values of K that I have supplied, I think I'm going to need a lot of zeros. So if I run that, whoa, stop. That was way too many zeros. I put way too many. It's freaking out.
6 zeros should be.
6 zeros should be enough. So again, what you're doing now is digitally asking the question, how long might this take to go to completion? Well, that depends on how much starting material you have and what the values of your K are. So again, we're going to stop here for now. Practice this part. This is a major point of what I've asked you guys to sort of do for first assignment. We will play with this again. So if you can't get this up and running, let's start off next class. We're going to go through the next piece of it, but I expect you guys to at least get this far to being able to build this much of it and visualize these points. I want you to practice how many zeros do you need in order to get an output curve. Again, that much? So that's not quite enough yet. What I did wrong, so this is a stupid thing. Look at how many intervals I'm doing. So what I'm doing is billions of small calculations. The way this works, right, is it's actually running all the equations, doing the differential equations here, calculating what the new product should be, starting that as an initial, doing it again. So having this many intervals is just a lot of freaking useless math, right? I'm being far too point. All right, practice that through, guys. I got a couple of minutes if there's specific questions you guys want to ask about this. Otherwise, I'll see you guys on Wednesday. Yeah, so I'm starting to get there, but yes, exactly. It should look like this. Boop. That. Boom. That's what it should look. Yeah, so it's basically 1 million seconds based on the Ks that we have in concentrations. This is how this goes. So what we'll do is we'll kick off at this one and we'll play the game of what if I add more catalyst? What if I do this, right? All right, thanks guys.